As everybody is coming in today, first, thank you. Most of you did a great job on the lab. A few of you I didn't get. So let me just verify that you did not turn it in. Jack Johnson, you're one that stands out. Did you turn in the lab?
No, I couldn't turn it in. Blackbaud kind of not working.
Okay, I just want to make sure if I should be looking in my email or in my, all right.
Yeah, I'll send it in an email.
Did you get to do it though?
Yeah, I started it.
Okay, well, you can send it in an email. John Kalizi.
I never got anything from you, so I had no idea what I was doing.
Oh, John.
I kid you not, I don't get your emails.
That feels
What
great.
email do we have at
Oh,
school?
I don't know, but I checked, and
I
my
think our fearless leaders making excuses instead of arrangements.
John, project due tomorrow.
Huh?
See, didn't know it.
Half your grade due tomorrow.
Hey, John, first of all, there's a blank space in Blackbaud. That is the one thing.
Why would I have gone? I didn't know that it was a thing. Why would I have checked Blackbaud?
You should be checking Blackbaud every day. That's where.
Yeah, I check for the classes that tell me I have. All I remember is that on the call last time he said that if we needed to come get stuff, which I did, I came to the school and got like the battery, like Stallings with him. He can say that I was there. I got the stuff.
Oh, did you guys pick up a motor? All right, well, I mean, it's just something I want you to be able to do. So what I'm saying is on Blackbaud, you can always go to the course documents, and that's where you'll find everything, telling you what we did for the day. And so if you feel like you're not getting the emails, go there. Let
me just check Intro to Engineering.
Resource. Tony, what did you have to say?
Ma'am, I got to leave in T-minus 6 minutes.
All right, DeAndre, sorry, you're going to have to watch the video later. And then Sam. I didn't get a lab from you, Sam. Did you submit anything, or are you aware that there was a lab? He looks like he's unmuted, but.
Well, are we turning in anything today?
No, but your homework will be the second half of the lab. There was a part 2. So get on the same. Jacob Dunleavy, attitude.
You're wilding right now.
Coach.
Part 2.
Attitude.
Oh my.
Should be rolling that head at me.
Every day, 2 weeks left.
Come on, boys. Come on. To the end.
Coach, I built my switch.
Did you?
It's a paper clip, see? I did it.
Yeah.
Well, no, both ends have to be connected to a conductive surface.
Right, Coach, look. I did it.
Let me see. Oh, I love it.
I know, I'm awesome.
Brass fasteners?
Yeah, I took the pins from my name tag thing.
Oh.
That's smart.
Let me turn that on. I'm proud of you, Sean. I'm very proud of all of you that turned in your labs. Excellent.
Yeah, see?
Look at that. Yay. So Hayden and John, did you guys pick up the little motors?
Yeah, we picked them up.
I grabbed a motor too.
Did you? Cool.
I'm special.
Okay. All of you guys, that's a Benedictine, so I'm glad you were able to go get that. If anybody else needs supplies, I also put some batteries there and lights, all of that stuff. Anybody that might live closer to Mechanicsville, Tim, I know that's your case. Ethan, you guys can pick those up from me if you would like. Just send me an email.
Is it too late for us to submit supplies to you?
Oh, no. I mean, we're going to use them. So we need to be able to have those supplies. So if you did not get a grade yet on those supplies, I'm definitely still going to take those.
Okay.
All right, so today's focus will be, what did we learn in the lab? What information did we get out of the lab so that we can go forward to build, as you see with Sean, the actual room. So the goal is that we will eventually build a room. All right, DeAndre, no thanks.
We're going to build a crib?
Sorry.
All right, so what we're going to do is when we build this, we want to actually build the room. And I'll show you at the end of class for some inspiration, one that I have that just to kind of, give you an incentive. And now the whole goal, truly, Jacob, we have to get through some classes, right? So number one, we want to learn about something we don't know much about. something that is practical. You guys all use your electricity, all of you. And I hope that you have a goal that you will be a homeowner someday and that you understand a little bit about the wiring in your house, because it actually is very simple. We've done some work here that required us moving some lights from one place to another, and it was pretty neat to be able to know how to do that ourselves. So anyway, it is actually very, very simple. So just a couple other comments. Daniel, I see you on here, and Timothy. I also did not get labs from you two. So if I did not get labs from you, you can still turn it in, and that's the expectation because it was a lot of points. And I want to make sure you get those turned into me. A couple comments. Ethan, your lab, is he even here with us today? I don't see Ethan today. Oh, yep, there you are, Ethan. I didn't see any measurements. So you didn't complete all of your measurements. You'll see what we're talking about today. So if you want to stay after a minute, I'll explain. And Nate, as you watch today, I think your last 4 circuits may not have been built correctly based on the numbers that you are showing. So based on your measurements, I'm not so sure that you did those correctly. And Jack Hall, you are missing one of your pages. So all that I was able to open up is 1 page, okay? Okay, so everybody else, are we ready? DeAndre, since you have to leave and you like to be so close to the camera, how about you leave us with our prayer for today?
Oh, my mom said I could leave at 1:15 now.
All right.
I bet we finna pray. In the Father, Son, Holy Spirit. Hail Mary, full of grace, Lord is with thee. And that's where y'all end it. Y'all don't want to end it? I don't know the rest. So.
Blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen.
Bet. We a lot.
Thank you.
You're welcome.
Right.
Coach,
All
I have
right.
a question real quick.
Yes, Logan.
Why do I have a 5 out of 10 for supplies?
Because you suck.
I think on that day you only showed me lights, right?
I had lights in a box. And what else do I need? Batteries?
Batteries, aluminum foil if you have. You
right,
can still show it to me. That's fine.
Hey,
All right,
Coach.
I'll get those.
Okay.
Coach.
Jacob Dunleavy.
I got all my supplies. Do you need to see it?
Yeah, let's, I know I have a lot of, okay, here's the deal. I have a lot that I want to go through today. So if you owe me some supplies, if we have time at the end of class, show it to me then. If not, I'll get it from you on Thursday. Okay? No points off because it's much later. I know what I want to get a lot done today. So if you were missing some, I'll go back and check who that is and make sure I look for that on Thursday. Okay? All right, so real quick, April 27th, 28th, right? April 28th, mustard seed. Develop the ability to say everything without saying anything. Action is the loudest voice. Jacob Dunleavy. Rolling your head is a loud voice.
Love you.
Okay, so action, speak loudly. All right, gentlemen, today, really pay attention. I'll be honest, not until I went to college and I was actually assigned to develop lots of electrical labs for undergraduates when I was in graduate school, did I really get appreciation of electricity. And once you get comfortable with it, it actually is, it's so cool. I think it's really, really cool. And the wireless world is even more amazing. So I just want to give you the basics so you have some background. So when you move on into college, you're not totally out there not knowing anything. Or if you never even study this again, it's just very practical. So what I would like to do today is discuss a little bit more on what you saw in the lab. Okay, so we want to talk about what did you see in the lab and what information did we get from it. So to do that, and those of you that did not do the lab, my goal is that you still go back and you do the lab. You're still responsible for all that information. Make sure you have that for me for a good grade. So it's a big, big grade, 30 points. That's a lot of points. So I'm going to bounce back and forth between the whiteboards and the lab that we saw and your write-up for it. So I want to compare 2 different labs. So first, 2 different circuits. So I'm going to go back and take a look at your, we'll do a screen share here. All right, so we're going to take a look at your circuit. Okay, so first of all, this was your lab write-up. Okay, so if I lose anybody, today's homework, okay, so you did this first part and you guys did really, really well on it. Those of you guys that turned it in did excellent. Hopefully, I know it may have taken some time, but hopefully you learned something. Tonight's homework is right here, part 2, and I'm going to explain that at the end of class. Very, very simple, should not take you very long at all. All right, but if I scroll down here.
When's that due, Coach?
It'll be due then on Thursday. Be very, very quick. You'll see. All right, so if we could take a look at our circuits that you had to build. As you notice when you built these, 1 through 4 were pretty simple. 5 and 6, and then we have 7 and 8, a little more complicated. So number 8, getting to our most complicated circuit of all of them. So this was in circuit symbol form. You were to build those. What I want to do is take a look at 5 and 3 to begin with. So right here, if we take a look at 5 and 3, what we notice about them is they both have the same voltage, they both have 2 switches, they both have 2 light bulbs, right? So they look exactly the same. So if I go back in here, here's our 2 circuits. I built them in the simulation side by side so we can compare the 2. The difference on mine, just for the sake that you guys aren't copying my numbers, I put each battery voltage as 12 volts, but we should see the same pattern, okay? So what I want to notice first of all is how bright are the bulbs? How many of the switches have to be on, okay? So in circuit, what looks like circuit number 3, if I turn on this first switch, I close it. But unlike water that would continue to flow through here and just come out of this opening right here, the electrons don't do that. They don't even flow. So this light bulb does not go on unless both switches are closed. And that's our complete closed circuit. So if there is an opening anywhere, doesn't matter where, everything shuts off. So for this type of a circuit to work, everything must be on. The bulbs are of the same brightness, mainly because they have the same resistance. So if I put our values in here, the resistance of all of our bulbs are 10 ohms. So that's going to be true throughout this lab. In this lab, you weren't to change those resistances. But if I go over here and I take a look at circuit number 5, and I close this one, it works without this one being on. And it is very bright compared to these, even though both batteries have a voltage of 12 volts. And I have 2 light bulbs. So we have 2 different scenarios here. Same stuff, but connected in a different way. If I shut that one off and turn this one on, it also works without the first one being on. If I turn on the first one when the second one is on, it has no effect on that second one. So notice when I turn this one on and off, the second one does not get any brighter or any dimmer. It has no effect. However, if you look carefully, when I do turn on both of them, look what's happening coming out of the battery. It seems like the electrons start flowing faster, okay? Which is interesting because there are 2 things in both circuits. Okay, so let's talk about what we're seeing there. The brightness of the bulbs, how the electrons are flowing, what's going on in each one of these circuits. Okay. So, did everybody see those circuits? All right, I'm gonna go to my whiteboard now and let's write down some things. So this will be it. These are pretty much your notes for this unit. Your unit might involve questions where I'm going to build a circuit and you're going to have to tell me what do you think is going to happen in those circuits. So let's take a look up here. So if I were to redraw these circuits, okay, let's take a look at circuit number 3. So that's just for reference on your, oh, I see that major glare there, right? Can't see that. Hopefully that helps. Okay, So, hold on here 1 second. Okay, so circuit number 3. I made this 12 volts. We had one switch, a light bulb, another switch, another light bulb, and it came out and went back to the battery. So that's what we are seeing in circuit number 3. In circuit number 5, you had 12 volts, except in your lab you had 6 volts. So in my simulation, I'm setting up 12 volts. We had 2 switches and 2 light bulbs, but they were connected differently, okay? The most obvious difference, okay, Logan, what would you say is one of those differences between these 2 circuits?
It's got 2 separate like things compared to circuit 3. There's
Okay.
another
2.
vertical.
Okay, another pathway. So if we go back to what the definition of a circuit is, we have 2 pathways here, but only 1 pathway for the current to go. Good. So one analogy is we have 1 pathway. Over here we have more than 1 pathway. Excellent. All right, Sean, what can you tell me about how these things have to be on over here compared to these? What effect does one switch have on this circuit compared to over here?
On the third one, if you undo one of them or cut off any of them, it cuts off the whole flow of the electrons.
Very good. So over here we would say everything must be on, right? Including a light bulb burning out. So if one of these light bulbs burns out, everything's going to go out. Sean, over here, what would you say?
You don't have, I don't think you have to have any of the switches necessarily on, right?
Correct. We would say these are independent of one another. So each branch is independent of the others, right? Each branch is independent of the others. Very good. All right, so those are the obvious things that we were taking a look at. Now what I want you to think about in terms of current and voltage. If we look at these, so they both had 12 volts, and this should be true in your numbers, okay? So if you remember, voltage was the energy, right? It's how high I was lifting those marbles. Current was the actual marbles. So if I take my marbles again, here's my marbles. If I think of my marbles works, I have a whole bunch of marbles, right? That's the current. How many of these are flowing through the wires? How high I lift them in order for them to fall, right, would be the voltage. So I'm giving them energy when I lift them up. Over here with my battery, I take these marbles and I lift them to give them 12 volts of energy. If I come over here and I have to fall back down, when I fall down, I fall part way in each one of these because it's only one path. So if I fall through here, I lose some of my energy and I don't have as much energy to give to this one, or somehow I split that up. Over here, when I lift up my marbles, when I come across here, the marbles that are here and the marbles over here have the same distance to fall through. So what we see right away with voltage, if I go back to my video, my simulation, and I take voltage measurements, what I notice here is, if I bring my voltmeter out, we know that the voltage of the battery is 12 volts, right? So on this circuit, so we have 12 volts. The voltage that goes across, let's do bulb 1 first. I put my probes there, 6 volts. So if the electrons come through and they lose 6 volts of energy here, they have 6 volts left here. So that would make sense because I'm falling through that path. It's like I fell part way. Watch what happens though. Just know that that voltage does not have to split up evenly. If I change my resistance, let's make this one maybe 40, and I change my resistance of my bulb, here my voltage is 2.4. Altogether that was 12. So over here, 12 minus 2.4 gives me 9.6. So 2.4 and 9.6 still adds up to be 12 volts. So they will split up that voltage, not evenly, but they will split it according to each one of their resistances. This one had the higher resistance. If I dial it back down to being the same resistance, about 10, right, is where we were. They both get the same voltage. Over here, our voltage of the battery was 12. Since the electrons that go through here only have to fall through one thing, they have all of that voltage to give up to the one element in that path. These also have that 12 volts to give up over here. So the voltage is the same in each one of these branches because that's the height that they are basically going to fall through. So that's voltage. Voltage is energy. You can look at the energy as how far do they have to fall. The current, however, if we go and take a look at the current, is the actual marbles flowing. So if you just look at the circuit, it should make sense that the current that comes out of the battery must go through the first bulb and must go through the second bulb because there's only one way for it to go. So the current that comes out of the battery, 0.6, bulb 1 gets 0.6, and bulb 2 gets 0.6. Over here, the current that comes out of the battery is 2.4. But once it hits this spot right here, it splits up. So the current that goes through here is not the same as the current that goes through the second path. It splits. Here that is 1.2 and 1.2. 1.2 plus 1.2 come back together to give us our 2.4, right? Same thing is true here though. If I make this resistance more, I change the total current coming out. However, that current that comes out still adds up to be the total current. 1.2 plus 0.47 gives us 1.67. So depending on what's in each branch would make a difference on how much current goes in each branch. But the current in each branch adds up to be the total current. Okay? So that's the important stuff that you saw in this lab that you were doing in the simulation. So let's go back to our whiteboard and write this down. Okay? So if we go back to our whiteboards, in terms of voltage, what we noticed over here is the voltage divides. Mathematically, we would say our total voltage is equal to the voltage of bulb 1 plus the voltage of bulb 2, and so on. If I had 3 things there, they would split it up. If I had 5 things, they would split it up. Keep in mind, that's not necessarily evenly. They simply split that up. Okay? If I go over here, Hayden, do you remember what do we say about voltage on this side? Did it split up?
What?
What happened to voltage in this circuit?
I don't know. What do you mean?
So the voltage here, 12 volts, what voltage did I have here?
Oh, 6, I think.
Over here I had 12 and then 6 and 6. So this was 6 volts, 6 volts. So remember, I lifted up 12 and I go through 6, 6. Over here, I lifted up 12. What do I give up here?
6.
No.
Oh, 12.
12, 12. I have all of that to give up into this branch. What about over here?
12.
12. It has just as much to fall through, right? So because it's different current, and again, you think of voltage as being lifted and you fall back down, be lifted and you fall down. 6 volts, because you're splitting up that path as you fall down, 12 and 12. So mathematically, we say voltage is the same. So V total equals V1 equals V2. They're all equal to each other. But I want to make it clear here that 1 and 2, and we'll see in circuits 7 and 8, we don't want to think of 1 and 2 as bulb 1 and 2, but rather branch 1 and 2. So where 1 and 2 are branches. So in this type of a circuit, each branch gets the same voltage. In terms of current, which is the number of electrons coming out. Right? Colin, what can you tell me about the electrons that came out of the battery compared to what goes through each bulb?
Half of it when it leaves the battery, it's 12 volts, but then going through the branch things, the light bulbs, that's reduced to 6.
Okay, so we're not talking about voltage now, we're actually talking about the current. So how many electrons coming out of the battery go through the first bulb, and how many go through the second bulb? What can we say about the electrons, which is the current? Since there's only one path, one road.
They're all going that one way.
Correct.
There's only one way for it to go.
So if I send out 2 amps of current, how much current goes through the first bulb?
2 amps.
2 amps. How much goes through the second bulb?
2.
2 amps. So in a sentence, I would say current is the same, right? So if current is the same, I total equals I1 equals I2 equals however many things I have in that circuit. All of my current is the same. Whereas over here, the current that comes out of the battery, I'm going to draw these as 2 different colors. Here comes all my current, right? What's going to happen here? Some of it goes there, some of it goes over here. Both of it goes back to the battery. So here comes all the current. Sam, what can you tell me the current does right here? Sam Slade, you with us? All right, we'll go to AJ. AJ, what happens to the current when it reaches this point right here?
It stops and it goes back the other way.
What do you mean by it stops and goes back? So here
Well,
comes all this.
It just keeps flowing to that one spot, but it stops there.
What do you mean one spot? I have.
It wants to go down.
And some of it does.
And some of it probably goes all the way around.
Correct. So some goes down, some of it goes around. So what would we say it does right here? It has to
disperse, I guess.
Disperse, split up, right?
Split
so it
up.
has to split up. So what happens to current in this type of a circuit? Current divides. And we'd say I total equals I1 plus I2, and so on. Again, where subscripts of 1 and 2 over here mean pathways. Okay? These characteristics fall into a category of what we call parallel circuits. So just lift that up a little bit. These are called parallel. So if I say, build me a parallel circuit, I need these characteristics. The voltage in each branch is the same. the current's going to divide, right? There are multiple paths that work independent of one another. Over here, if I want these characteristics, where current is the same all the way through, the voltage divides up, and I have one path where everything must be on. This is called a series circuit. And I'm sure you've heard those words before, series and parallel. Now you know the importance of them in terms of voltage, current. Okay. How's everybody doing there? Do I need to move? You all can finish?
Good.
All good? All right, so if those are true, let's take a look at what we saw in circuits 7 and 8. So sometimes when we build circuits, we want certain characteristics here. So think of all your electronics, right? Your speakers on your radios or on your, your JBL speaker, whatever. You turn it up, you make it louder. How am I making it louder? I'm making it louder because I'm controlling how much current comes through that circuit. By pressing that button, you're changing the current that comes through. By changing the current, you're also changing the voltage and so on. So everything depends on voltage and current. That's what gives us our power in our circuits. If I go to cook myself dinner tonight and I have to turn on the stove and I want to go from high, boiling the water, to turning it down to just simmering, what I'm physically doing as I move that switch, right, is controlling this. And that's what I'm doing in my electrical circuit. So Sean, as nice as that switch is you made, that'll turn it on and off. Some switches will actually change the amount of resistance in the circuit in controlling how much voltage and current comes in. So that's our whole goal here, is to understand the relationship between voltage, current, and resistance. So let me go back to this, our circuits. Okay, any questions or comments on what we saw here? So again, look at the pictures. Here comes the current in circuit number 5. Okay, let me do a little drawing on here. So right here in circuit, okay, let me move that out of the way. In circuit number 5, the current is splitting up, right? This electron that's flowing right here very slowly eventually goes in, loses its energy through that path, keeps on going, and then goes back to the battery. It never goes through the second bulb. That's why it has all of its energy to give here. Whereas this electron that's flowing right now, over here in circuit 3, does go through the first bulb and loses some of its energy, so it doesn't have as much energy to give to the second bulb as it goes through. Okay, so that's, if you think about the definition of voltage and current, that should all make sense. Think of voltage as how high these electrons are lifted. The voltage lost is how far they have to fall down. The actual current is the actual number of the electrons passing through the wires. So when we take a look at a circuit like number 7, you should know whether your numbers make sense or not. So at the beginning of class, I'd mentioned a couple of you that based on your numbers that you turned in for the lab, I'm not sure you built this circuit correct. So let's take a look at this. First of all, Tony, what type of circuit would you say that I have here? Parallel or series?
Series.
Why?
It has 2.
Okay, well, there's actually 3 light bulbs altogether. So this is a little bit of a tricky question, because when you say that it has 2, it has 2 what? Pathways, light bulbs?
Parallel.
Okay, that was Jacob Dunleavy, I think. Parallel?
Yeah.
Okay, and why do you say parallel?
Because it looks like the other one. Like it's got like 2 different like vertical pathways.
Okay, so right here I have a choice to make, right? If there's any place where I have to make a choice, that decides my parallel part. Parallel means you have a choice. But if there's any place where I have to go through something to get to something else, then this part, Tony, is what type of circuit? Did I lose Tony? You might be still muted, Tony. So this section, Tony, what's this part of the circuit look like? What would you say? Series or parallel?
Parallel.
No, there's a reason I asked you. What'd you say for your first question?
Series.
And why is it series? Because I go through this bulb, what do I have to do? I have to go through the first bulb to get to the second bulb.
Yeah.
So this type of circuit is what we call a network circuit, which is what most circuits are. They actually is a combination of the series and parallel. Why would I want this? Because this will follow the series rules. This path and this path are parallel to one another. So when I have to choose which way to go, those I would say are parallel to one another. Okay? So because of that, they should follow the rules of series and parallel. So first of all, if I turn this one on, this one does not work because it's in series with the second one. So I need both of those to be on for it to work. I do not need this one on for those two to work because this one is in parallel with these two. But when I turn this one on, it should not affect these two. But instead, the only thing it's going to affect is the current that comes out of here. If it does not affect these two, then these electrons that are going through here need to stay moving in the exact same way. So when I turn this one on, the only choice that can be made is that the battery sends out enough to continue to feed this branch the way it was and now feed this branch. So the effect of having this one on is that the battery now has to send out more current. But let's take a look at our voltages. If the voltage of the power supply is 12 volts, just like we had in our first two circuits, this one is on a path all by itself, right? So Timothy, how much voltage do you think is going to be across this bulb?
Shouldn't it still be 12 volts?
It'll still be 12 because it's in a pathway all by itself. Very good. Timothy, how much voltage is across each one of the other two bulbs? What's going to be across this bulb?
Does it divide or is it still?
You tell me, what type of circuit is it? Series or parallel?
It's series.
So what happens to voltage in series?
It's remains the same, right?
Nope.
No.
Write,
okay.
Write any of those notes down. Voltage in series will, and don't memorize it, think about it. It's like how far the marbles have to fall. Here they go. They're up here at the same height, right? And now they're gonna fall down. How far do they fall to go through the first bulb?
6 volts.
Halfway, 6 volts. There you go. Now what do they have left to give to the second bulb?
6.
6 volts. So you can see why I love electricity, guys. It's so easy. It's that easy if you think about it and make sense of it. And it turns out perfectly. The numbers always turn out perfectly. Across the entire branch, though, is 12 volts. Because if I didn't know this had 2 bulbs, and instead I just had something there, across the branch is 12 volts. Within the branch, you have something in series that's going to split it up. Good. All right, let's see. Does the current follow our rules? All right, so if I come over here and I measure current, so Jack Hall, 1.8 amps of current is coming out of the battery.
What'd you say?
Now we're talking about current. If 1.8 amps comes out of the battery, and then I measure the current that goes into here is 1.2 amps, how much current should I expect to have over here?
0.6.
0.6. Why? Because 0.6 and 1.2 add up to give me 0.8. I would not add up 0.6 plus 0.6 because this 0.6, this electron is exactly the same as this one. So I don't count it twice. The current that goes through the first bulb is the same as the current that goes through the second bulb, but my total current is the current that's in the branch over here, right? Which is 0.6 plus the current in this branch, 1.2, to give me 1.8. Excellent. All right, hopefully you're all following that. Let's take a look at circuit number 8. Does this one make sense? Okay, everybody take a look at that and you tell me what type of circuit do we have? What's in parallel, what's in series? Is it all series, all parallel, or that network circuit where it's a combination? So Ethan Fox, what do you think here? What type of circuit would it be?
Would it be like both of them?
Both of them, okay. What would you say is in parallel with one another?
The two going down.
Okay, these two that are here, right?
Yeah.
How do I know that? Because if I come out of the battery, I have to go through this, right?
Mm-hmm.
Here's where I make my choice. So whatever is on the path of where I make my choice, we say this path is in parallel with this path. Bulb 1, we would say, is in series with both of these bulbs. So bulb 1 is in series with these two bulbs. If that is true, then our rules must still remain the same. Bulb 1 follows the series rules, which is the voltage that comes out, or the current that comes out of here, whatever that is, must be the current that goes through here. This bulb must be on and always working. But down here, these two are in parallel, which means they should have the same voltage, and the current that goes through them that comes in here out of the battery splits between each one of those. So first, I can turn on the first bulb, right? This one is working, so it allows this one to work. And right now, it looks like I just have a series path. All right, Nate, the big question of the day. Power, which is how bright a bulb is, depends on current and voltage. When I turn on this third bulb, how bright will the second bulb be compared to what it is right now? And how bright will the first bulb be compared to what it is now? And everybody think about that, because this is a great quiz question. How would the bulb change?
It'd be less.
Okay, you think the first bulb is going to get dimmer.
Yeah.
What about the second bulb?
It'll be the same.
Why?
Because that one's in the parallel.
Okay. And why do you think the first one's going to get dimmer?
Because that one's en route to, once you connect the other one, it goes through that route.
Okay. So the effect of this one is going to be to take away from the voltage and current of this one. That's what would cause it to become dimmer. The effect of turning on this one is it's not going to do anything to this, change voltage or current. Is that what you're saying?
Yes.
All right, everybody ready? You all have your own answers. See if you're right. What happened there?
The opposite.
Just the opposite. Okay, now let's think about why. And this is what science is, right? Science is we have an understanding of something and it has to work for everything that we see. And if it doesn't, then what we were just talking about doesn't make sense. So Nate's thought was these two are in parallel, so it's not going to have any effect on this one. Good thought, right? However, this one is now in series with both of these paths, okay? So by turning this on, it made this one become dimmer, which means I either affected the current or the voltage across here. So let's take a look at that. If by themselves, this has, we know, 12 volts, right? Because that's what we connected it up to. Since this is just pure series, each one of these should have 6 volts, right? So they each get 6 volts. The amount of current coming out is the same. So they both got 6 volts. If I take the current, right now with that on, my current is 0.6. But when I turn this on, remember what's going to happen right here. This is supposed to stay about the same. But what happens here is I now have to feed this branch, which means the battery is going to have to send out more current. If the battery sends out more current, so watch this, I'm going to put my meter right here. So right now I only have 0.6. If I turn this on, it jumps up to 0.8. So now I got more current coming out, which would explain why the first one got brighter, because now it gets more current going through. But why did this one get dimmer? So remember previously it had 6 volts, but in this case, it's only getting 4 volts. So the effect of turning this on decreased the amount of voltage that each one of these branches got. And that's because it increased the voltage that this first one got. Remember, it only had 6 volts when this one was off. So if I turn that back off, this gets 6 volts. If I turn it on, that now got 8 volts. Why did it get 8 volts? And the reason is more current went through it. So voltage, current, and the element have a relationship with one another. And since this one now got 8 volts, what we do know is that only leaves 4 volts left in these electrons that are passing right here. Because altogether we had 12 volts. If this becomes 8 volts, this is only 4 volts. So now I only have 4 volts to give to each one. All right, we are running short on time. All right, so my point is the numbers still make sense if we go back and take our measurements. But it caught us by surprise because what we expected to see isn't what we actually saw. So we want to understand that a little bit more. So what I want you to do today, and I promise you, then we're going to start building our houses. So if you haven't gone over Benedictine to be able to get your motors, you're welcome to. Ethan, Tim, if you want to come here to get those, you're welcome to do that. Anybody else who's close to Mechanicsville, I'll have motors for you. All right, so with that said, I want you guys to do part 2. It's not going to be long. What you're going to do in part 2 is find out what is the relationship between voltage, current, and resistance. So it's a very, very simple lab. And here's how you're going to set it up. So let me share my screen again with you real quick. You're going to go back to your lab write-up, right? And you're going to read directions on how to do this part. Oh, it's not letting me get to my picture. I want this one. All right. You're going to set up a lab like this. Instead of a light bulb, you're going to put this resistor in. Okay, so that's a resistor. All you're going to do is then put in your ammeter right here. So you see where I have my ammeter? So I use this type of meter. Build your circuit. All you have to do is change your voltage and see what effect does changing my voltage have on my current. So as I dial up my voltage, I get different currents. I sent you all a link to be able to use a program called Logger Pro that looks like this. You can use this or you can use Excel. So in here I have my voltage, here's my current in the Y. Voltage, current, 9. And I change my voltage and I plug in my current. You're going to get a relationship here. And I want you to show me what that relationship is. So is it linear? Is it a quadratic? What is the relationship between voltage and current. Okay? So it's a very quick, I apologize for rushing here at the end, but if you had already done the lab, that should be an easy setup. You're setting up that one circuit with a resistor. You're simply dialing up the voltage. You can use Excel, you can use Google Sheets, or you can use the Logger Pro program that I sent you. The Logger Pro graphs it immediately as you're plotting it. And you can either do a screenshot of your work and submit that, or submit an Excel spreadsheet. Somehow you're going to submit to me what is the relationship between voltage and current. Okay? All right, lots of information. I hope you guys learned something today. And then on Thursday, we are going to talk more about how does this work in your house? What's going on in your house? So I want you to be paying attention. When you flip on a switch, do you turn on 2 light bulbs, 1 light bulb? Does one affect the other? Are they the same brightness as the light in the kitchen? And so on. Do you have any dimmer switches in your house? Maybe in your dining room or something like that. You might have a dimmer switch. Take a look at the wiring near your washing machine, your oven. Where is your circuit breaker box? What is the purpose of all that stuff? Okay? So we'll get to that on Thursday. We're out of time, so I will look at supplies for you guys on Thursday. Does anybody have any questions?
Can I talk to you for a second after?
Sure, absolutely. All right, everybody, have a great day. I'll see you Thursday.
Bye, Coach.
Bye.